2.6, distance time graphs. Now here's examples in distance and time graphs for you to understand a line of best fit and also understand how a distance and time graph is related to a line. A distance time graph basically shows an object's distance from a certain point, from a fixed point, over a period of time. So for example, somebody's standing in front of a sensor and moving back and forth, or mapping how far someone, from the moment you leave home to the moment you return home, or for example, even go to school. On distance time graphs, you would have time on the x-axis and distance on the y-axis. Okay, so on distance time graphs, you have a distance on the y-axis and time on the x-axis. Distance always depends on time, folks. So distance is your dependent variable, time is your independent variable. Distance depends on time. The dependent depends on the independent. So we have distance and time. So we have, for example, a graph that looks like this. What's happening when it's referring to a distance time graph? Well, the first line we'll highlight in blue. The first line indicates that you are moving away. So as time increases, distance decreases. So distance increases. I apologize, one more time. As time increases, distance increases. So what happens is as time goes on, you're moving away from the sensor and then coming over this way. As time increases over here in the red part, distance decreases, okay? And the last part, so in the red part, just like referring to the red part, as time increases, the distance decreases, so you're moving closer to the sensor at a steady rate. And then finally, the last part is going to be highlighted in green, and that green part indicates as time increases, distance remains the same, stays constant. So that means you don't move at all. Time is continuing, but you're not moving at all. So again, here your distance as time increases, your distance increases, you're moving away. Over here, as time increases, distance decreases, you're moving towards. So again, these are all at a steady rate. And then over here, as time increases, distance stays the same, so you don't move at all. So distance is constant. Okay, on that note, let's look at an example. State which phrase best describes each segment of the distance time graph. So here we have our distance time graph, looking at this, A, B, C, D, E, and let's look at the first phrase. No movement, fastest movement, slowest movement, and backward movement. So all of this, that's a lot of information, folks. I get that. So let's move back slowly. Here we go. And now we're going to look at no movement. Which one of these has no movement? Distance remains constant. That's right. That should be CD. Every horizontal line indicates that no movement has occurred in a distance time graph. Okay, so the horizontal line has a constant value. Okay, it's constantly the same. Fastest movement means BC in this case. Why is that the fastest? Because it is the steepest line. The steepest line indicates the fastest movement. The slowest movement, folks, is going to be AB. Why? Because it is the least steepest of the lines, the least steep. Less steep than any other one. It's more horizontal. if you want to say. So because it looks more horizontal, it's going to definitely be slower than something that is more steep or more vertical. Finally, the backward movement is moving backwards from the sensor. So this is moving forwards, this is staying the same, and this is moving backwards, back towards the sensor. And that would imply DE. You're coming back. All right, next part, example 2. These graphs show a person's distance from a wall. Describe the motion in the first graph, then explain how the motion changes in each subsequent graph. Okay, so we have our first one here. You'll notice that the person is so much away from the sensor, moving towards the sensor at a steady pace, at a medium pace, and then the person stands still, and then moves away from the sensor at a very quick, steady pace. Now, in comparison to the other distance time graph over here, where you have something like this, what can you say in comparison to this? Well, these two are still the same. So the person moves towards the sensor at a steady pace. The person stands still for a certain amount of time. So again, standing still. But then when the person moves away from the sensor, they're moving at a slower pace than before away from the sensor. This one is a very fast pace, faster than before, and this one is slower than before. And the reason you can tell is by the steepness of the line. Okay, another example, folks. What do you look at when you see curves versus lines? We've talked about nonlinear relationships and what those curves do. So, for example, this one is at a fast, steady speed. This particular line is quite steep, so it's a fast, steady speed. This one over here is at a steady speed, a regular steady speed, obviously slower than this fast one. It's not as steep. And then you have a stationary time, so at this point you're stationary, you're not moving, there's no movement. And then here, you're returning back to the start at the same speed in which you, maybe the same speed at which you started. Okay, so in this case, this might be a little bit faster than this, again, depending on the steepness. You're returning back to the start. So if you, for example, let's do a story. Someone leaves home at a steady speed, stops at the store for a certain number of time, turns around and goes home at a steady speed. So again, at a regular steady speed. Now, if the slope of the line changed, you could say faster or slower than before. And this one over here, this really funny one over here, is getting faster. What this means is that you are speeding up as you go on. Instead of going at a steady speed, a curve indicates that it is speeding up in terms of a distance time graph. All right, folks, let's look at another example. Describe a situation that corresponds to each distance time graph. So, here's an example. You move away from home and you travel at a slow, steady speed, and then you've increased your speed and you move at a fast, steady speed. You're moving away from the sensor. In this case, you're moving closer to the sensor at a steady speed. You stay stationary for a certain amount of time, and then you move away from the sensor at a faster speed than before. In this case, what you're doing is you're speeding up, then all of a sudden you start to slow down. And that, folks, is how you would describe each situation. So again, this one, speeding up and then slowing down. This one, moving towards the sensor at a steady speed, not moving at all for a certain amount of time, and then speeding up away from the sensor faster than before at a steady speed. This one, you're moving at a slow, steady speed away from the sensor, then all of a sudden you've increased your speed at a steady speed, moving faster away from the sensor. All right, folks, that's the end of the video. Have a numerical day.